Imagine you have two different capacity batteries and you want to wire them up in parallel. This 12 volt 100 amp hour and this is a 12 volt 200 amp hour battery. Now, if you connect a load, you would expect this battery to deliver 1/3 of the power and this battery to deliver 2/3 of the power. But is that actually true? Let's find out in this video. I'll measure the current through these two wires using a space heater and it will draw approximately 77 amps. With a 77 amp draw, we would expect this smaller battery to deliver about 25 amps and this one 50 amps. .77 amps. This battery delivers 47 amps. And this battery delivers 30 amps. That's not what we expect to see. So why is that? Internal resistance plays a crucial role in how current is shared between batteries. If you have different capacity batteries, the length of the wire doesn't matter as much anymore. The current draw depends more on the internal resistance of the battery itself. I'm going to break down how you can calculate it. First, we calculate the internal resistance. Then, using Ohm's law, we calculate conductance. And then we figure out the current. Finally, I will give you some practical advice about wire and fuse sizes. So now we're going to measure the internal resistance of each battery. It's important to isolate the batteries before doing this measurement. The measurement is actually quite easy. You don't need a lot of tools. We're first going to measure the voltage at the input terminals of the inverter. Then we will apply a load and measure the voltage again. And then we will divide this difference with the current going through the wire, which we already know is 77 amps. And the result will be the internal resistance of the battery plus the wires, the lugs and the fuse. Then we repeat it for a 200 amp hour battery. First I will start by isolating this battery from the other battery. Then I will measure the voltage at the input terminals. And we have 13.27 volts. Now I will apply a 77 amp load and do the measurement again. .39 volts. So first we had 13.27 volts and now we have 12.39 volts. If we subtract them, we get 0.88 volts. This is a voltage difference. And now we have to divide by the current, which was 77 amps. And we get 0.011 or 11.4 milliohms for this battery. Now let's test this battery. Again, we will measure the voltage when no load is applied. (13.27 volts). Now we will apply the 77 amp load. We will wait a second for the load to stabilize. Now we have 12.64. At the same 77 amp loads. So we had in the beginning 13.27 volts, and when we applied the load we had 12.64 volts, and the difference is 0.63 volts. Then we divide by the load of 77 amps and we get 0.008 or 8 milliohms. Now that we know the internal resistance of the battery, including the wires, the lugs and the fuses, we have to do one more calculation, and that is calculating the conductance. This can get a bit technical, so stay with me here. We will calculate the conductance of each battery in Siemens using the following formula. G equals 1 divided by measured resistance. For the 100 amp hour battery, this is 1 divided by 11.4 milliohms equals 0.0877 Siemens. And for the 200 amp hour battery, 1 divided by 8 milliohms equals 0.125 Siemens. Adding these together gives us a total conductance of 0.21 Siemens. And finally, we can calculate the current for each battery. For the 100 amp hour battery, we divide the conductance of the 100 amp hour battery with the total conductance, and then multiply with the current in the circuit. 0.0877 divided by 0.21 times 77 amps equals 32 amps. And for the 200 amp hour battery, 0.125 divided by 0.21 times 77 amps equals 45 amps. And now, when we measure the current again, these values should be very close to the calculated values. We have 46 amps and 30 amps. As you can see, these are very close to the calculated values. So what can you learn from this? If you wire your batteries in parallel and they have the same age, same manufacturer, and the cables are the same length, you can use a standard method to calculate the current. If your batteries have different capacities, you should use the second calculation, which is the more complicated one, because the internal resistance of the battery plays a more significant role. If you have the same capacity batteries, then I suggest using the same cable sizes everywhere. It simplifies everything. But if you are using bus bars, different cable sizes can be used. For example, with a 2000 watt inverter, the maximum current in the system is 2000 watts divided by 12 volts equals 167 amps. Then we have to figure out how much the inverter draws at the input, because it's 90% efficient. 167 amps divided by 0.9 equals 185 amps. For the 100 amp hour battery, we use the following formula. 0.0877 which is the conductance of the 100 amp hour battery, divided by 0.21, which is the total conductivity, times 185 amps, which is the max current in the system, and we get 77 amps. Then we multiply by the safety factor of 1.25 and we get 96 amps. And then the same formula for the 200 amp hour battery. 0.125 divided by 0.21 times 185 amps equals 110 amps. Then we multiply by the safety factor and we get 137 amps. For the 100 amp hour battery, we can use a 6 gauge or 16mm square cable. The fuse between the max current of the system, which is 96 amps, and the max current of the cable, which is 115 amps, is a 100 amp fuse. For the 200 amp hour battery, we can use 4 gauge or 25mm square. The fuse between the max current of the system, which is 137 amps, and the max current of the cable, which is 150 amps, is a 150 amp fuse. That wraps up this video about current sharing for different capacity batteries in parallel. If you found the video helpful, please give it a like. Thank you for watching, and I will see you in the next one.